This talk presents FedEx, an explainability framework for data exploration steps. Data exploration is the process of analyzing a dataset in order to uncover insights and discover interesting aspects of it. So, this is, for example, is the Spotify Challenge dataset that contains about 175K songs from the platform alongside some metrics such as acousticness, danceability, and the popularity column. Often, data exploration is performed in light of some analytical task. It could be, in our case, what makes a song popular. While data exploration can be performed on numerous platforms, a highly popular one is using scientific nodes such as Jupyter and Apache Zeppelin. So they are very convenient because they are web-based interfaces that interweave both code, visualization, and markups on the same place. Also, they are reproducible and easy to share on platforms such as Kaggle and GitHub. And most importantly, in our case, they also support data frame-based exploration via libraries such as Pandas. So while FedEx theoretically supports all kinds of analytical interfaces, it is particularly designed for data frame-based exploration. However, data exploration is a difficult process that requires domain expertise and experience. It is particularly difficult because of the three main challenges. First challenge is coming up with exploratory questions, so users don't always know what to ask in order to search for insights. The second challenge is composing queries. So even when they have an exploration question in mind, users still need to translate it into a structured query and execute it on the dataset. The third challenge, which is also the focus of FedEx, is to interpret query results. So once a query is executed, a main challenge is to understand the result, identify insights in it, and discover patterns. Consider the following example on the Spotify dataset. So let's say that the user executes a query that is equivalent to select star from Spotify where popularity is higher than 65. The result is about 7,000 tuples long, and the challenge is how to interpret this and what is interesting in the result set and why. FedEx produces explanation to such queries using a twofold process. First, as a human analyst would have done, it discovers what is interesting in the query results. Second, it detects which data subsets highly contribute to such interesting patterns. So a good explanation in terms of FedEx is to discover a set of rows from the input data frames that significantly contribute to a highly interesting aspect of the results. So for this example query on the popular Spotify songs, FedEx generates the following explanations. The first explanation detects an interesting pattern in the column year, as it significantly deviates after the filter. The strongest pattern, as detected by FedEx, is on years greater than 2015. We can immediately understand from this explanation that newer songs on Spotify are much more popular than older ones. The second FedEx explanation detects a strong deviation in the acousticness column. Now, FedEx discovers that high acoustic songs appear much less in the filter data, which means that they are largely unpopular on Spotify. Let's now review the FedEx system architecture. So, given an exploratory step Q, which consists of an input data frame D in, an operation Q, and an output data frame D out, FedEx operates as follows. It first evaluates the interestingness of the resulted data frame D out. We do so by computing interestingness score for each column in the output data frame. For filter, join, and union queries, we use a deviation-based measure that computes the Kolmogorov-Smirnov test score for each column. So the stronger the deviation is, the more interesting are the results. For group by operations, we measure the diversity of each aggregated column. We do so using the coefficient of variation. Intuitively, the higher the variance, the more interesting are the results. Now, recall that we are interested in detecting sets of rows from the input data frame that significantly contribute to the interestingness score of columns in the results. But explanation must be coherent and meaningful, so we do not want to calculate the contribution of random subsets of the data. Rather than that, we employ several sets of row partitionings that divide the data to semantically meaningful subsets. We use, for example, frequency-based partition for categorical data. We use partitions such as binning and equi-width histograms for numeric columns, and also divisions that are based on many-to-one relationships that can tie, for example, the column year in the Spotify dataset to the column decade. Now that we are focused only on semantically meaningful sets of rows, we can quantify their contribution to the interestingness of a column A. We do so using an intervention-based measure that evaluates the contribution of R to A as follows. It measures the difference between the interestingness score where R appears in the input data frame DIN and the case that it doesn't, so DIN minus R. So if this difference is high, it means that the contribution of R to the interestingness of A is high. And this is done for each row partition that we have. By this stage, FedEx has computed the contribution scores for each set of rows in each partition to every column in the output data frame DOut. We next want to balance the trade-off between contribution and interestingness. We do so using the skyline operator, which outputs only the dominating tuples of sets of rows and columns, R and A, that are dominating, right? So, namely, there is no other set of rows, R tag, with a higher contribution to another column, A tag, which is more interesting than A. Last, for each explanation in the skyline set, FedEx generates a caption visualization using a template for each interestingness measure. In this example, we can see a generated explanation to a group by operation on the popular songs data frame using the column decade and the aggregation mean. FedEx shows that the column tempo is interesting as it shows high variance. The most contributing set of rows is decade 2020, where its tempo is 1.6 standard deviation higher than the mean. We can immediately understand from this explanation that newer songs from the current decade are of a faster pace than older ones. Let's briefly survey the experimental evaluation we performed for FedEx. So for baselines, we use the following approaches. First, we use the interestingness only baseline, which is in fact a lobotomized version of FedEx, which does not calculate the contribution of sets of rows to the interestingness, and rather than that, only discovers the interestingness column in each result set. The second baseline is CDB by Vardag et al., which is a system that generates a bar chart visualization based on interesting discovered group bys on a given subset of the data. The third system is RAP, which is an open source platform for insights discovery. We also use a manual baseline in which we ask 3 expert data analysts that we recruited to manually analyze query results and build an explanation for them. Our user study was composed from 25 participants with varying degree of analytical expertise. For the experiments, we used 3 datasets from Kaggle: the credit cards dataset, the Spotify dataset, and the products dataset. We composed for each one 10 queries, 5 filter and join queries, and 5 group bys. And the queries were inspired by real-life exploration notebooks that were published on Kaggle for each dataset. Users were asked to rate each explanation from each baseline according to how coherent and understandable it is, how insightful it is, and how useful the explanation is in assisting the users to understand the query results. While the results show that naturally, manual explanations that were generated by expert users indeed obtained the highest rating, but FedEx is second to it and consistently achieving higher ratings than the rest of the baselines on all 3 datasets. However, when considering running times, see that while explanations generated by experts obtain higher user rating, see that the times it takes them to construct an explanation is naturally higher than FedEx. We use here an optimized version of FedEx called FedEx sampling that calculates the interestingness score on a sample of the data rather than the full results. We observe that it yields identical explanations as the full FedEx, yet operates faster. Also, when compared to CDB and RAF, see that FedEx scales better and able to return explanations for a dataset of 10 million rows in 63 seconds only. Next, we want to share that FedEx is now a part of an open source library called PDExplain. PDExplain is a new Python library that wraps pandas and allows users to use FedEx seamlessly in their analytical workflow in a Jupyter notebook. So it wraps pandas data frame, and as we can see in the example here, the user loads a dataset and then makes a similar query to the one we saw in the example today, and then uses an explain method, which is performed by pdExplain, and the explanation is provided in line. FedEx also contains advanced features such as allowing users to obtain a prefixed number of explanations displayed in one row, and also knows how to eliminate correlated explanations. Thank you very much for listening to our talk, and we invite you to reach out to each of the co-authors and provide us with feedback or ask questions. Thank you.